Everyone, we're going to look at number 24 in section 5.1. For this problem, we're going to find a formula for R sub n. So this is the right-hand, approximation with n subintervals. I'm actually going to use lowercase n in my problems. You can use uppercase n as well. And we're going to compute the area under the graph of this function f of x equals the quantity 11x squared over this interval, -1 to 5, as a limit. So we'll take the limit as n goes to infinity. And then give your answer as a whole number or exact answer. When they say whole number, exact answer, of course, whole number is 0, 1, 2, and so on. Exact number, if it's a fraction, would be like 1/3, as opposed to writing as 0.333. So, basically fraction form. So make sure that makes sense. Okay, again, your numbers may be slightly different on this problem. First, I want you to note the function 11x quantity squared is really 11 squared times x squared, or 121x squared. I think that's a little bit better form. My interval is starting at -1 and ending at 5, so my value of a is -1, my value of b is 5. So delta x, right, b minus a over n, is going to be 6 over n. That's the width of each subinterval. My right-hand endpoints, right, are a plus I delta x. A, again, is -1, and delta x is 6 over n, so I times 6 over n gives me 6i over n. So -1 plus 6i over n. That's the CI. So remember our right-hand sum. We're going to sum for over all n subintervals. The height of the rectangles, that's f of CI, times the width delta x. The width is constant, all right, 6 over n, so I put that in. And then f of CI, right, we just evaluated here, so it's f of the -1 plus 6i over n. Okay, remember our function is this simplified 121 times x squared. So if I plug this in the parentheses right into the function, I'm replacing x with this quantity. So it's 121, and the in parentheses, the x is this quantity squared. All right, so here's f of CI times delta x. Okay, and then what is this quantity squared? So be careful. It's this times this, so foiling that out, I get -1 times -1 is +1. The outer and inner terms are -6i over n, so they add to -12i over n, and the last times last is 36i squared over n squared. So be careful when you square that out. Now I'm going to do something a little different because these numbers are real big. The 121 times the 6 over n, I could distribute it through this. I'm going to go and factor it out, right, using the properties of summation. So if I have the summation of a constant times a variable expression, of course, the variable here in these problems is I, right? N is a constant for any fixed n. We're looking at these summations. We're going to later, of course, take the limit as n goes to infinity, but we need to first get an expression for R sub n. So if it's a constant c times a sub I can factor that c out in front of the summation. So these are the two linearity properties that we make use of. So I'm going to do that. 121 times 6 is 726. You might need your calculator to do that. So I'm going to factor out 726 over n. That's what this is right here. And then what's left, the summation, everything here we multiplied out. So I'll put that in there. Oops, I made a mistake. Okay, then I'm going to make use of these linearity properties to break the summation out, right? So summation I equal 1 to n of 1 minus the summation I equal 1 to n of 12i over n, but the 12 over n is a constant multiple for that sum, so I'll pull it out of there. Just out of there. Don't bring it all the way out because it's not in front of this summation. Okay, plus summation I equal 1 to n of this, but then the 36 over n squared can come out just outside of this summation, not outside of the whole thing again. Okay, so what do we do here? Well, now we're left with these power sums, right? So as I said, I will provide you with the formulas for these on the test. You should look on the sheet that I did in the lecture in the class to see what these are. Summation I equal 1 to n is n squared over 2 plus n over 2. And the summation I equal 1 to n of n squared is this expression here. Okay, so again, these will be given to you, but this is what these expressions are going to be equal to. So now that I've evaluated my sums, I haven't expressed in terms of n, I just need to clean everything up. Oh, so one other thing. What is the summation I equal 1 to n of 1? Well, it's just n times 1, right? Because we're basically adding 1 to itself n times. So n times 1, of course, n. Over here, I'm going to do some distributing, the negative 12n distributing over these two. And when I multiply negative 12 over n times n squared over 2, I have 6n, right? I'm left with 1n on top. 12 divided by 2 is 6. Negative 12 over n times n over 2 gives me just negative 6. The n's cancel. Negative 12 divided by 2 is negative 6. And then I'm going to distribute this over these three terms. And when I do so, you should note the first 36 over n squared times n cubed over 3 gives me 12n. 36 over n squared times n squared over 2 gives me 18, right? The n squareds cancel. 36 divided by 2 is 18. And then 36 over n squared times n over 6 gives me 6 over n. 36 divided by 6 is 6. N over n squared is 1 over n. And I can clean this up. I've got n minus 6n plus 12n. So that's a negative 5n plus 12n is 7n. And I have negative 6 plus 18, that's 12. And then plus 6 over n. So this right here, this whole expression here is r sub n. And I can get a final expression for r sub n if I now distribute this big 726 over n through these three terms. Okay, so I chose to remember to factor this whole thing out at the beginning. You could distribute through all of these, and then you would have different quantities outside of each of these sums. It would behave the same way, and you would end up with the same final result that I have here. So 726 over n times 7 over n, the n's cancel. 726 times 7 is 5,082. 12 times 726 gives me 8712 divided by n. 6 over n times 726 over n gives me this quantity over n squared. Okay. And so this right here, this, I'll just sort of circle this quantity here. That is your r sub n. Okay, so the question was in this problem, what's the limit as n goes to infinity of r sub n? All right, so it's just the limit as n goes to infinity. We just put that in here. And notice these two fractions, right, since they're dividing by n and n squared, these are constants up top. They're both going to go to 0 as n goes to infinity. And so the limit is just 5,082. And so that is the answer to this problem. So I hope that helps. If not, you can just say something to the goat.